Alright, I'm gonna try hard to talk about the thermodynamics quiz and give you hints without straight up telling you the answers. So, alright, here we go. Question 1. Things to think about are phase and size. Question 2. Let's recall the equation for change in entropy. Delta S equals Q over T, where Q is heat and T is temperature. Right. Order is a word that's thrown around to describe entropy. Higher entropy means more disorder. Lower entropy means more order. Okay, so yeah, there's two things that'll drive a reaction toward the product side, and that is if entropy increases and the change is positive, or if the enthalpy change is negative and heat is given off. Okay, I think I'm going to repeat what I said for the last question for this one. Yeah, what'll drive a reaction forward is an increase in entropy or a decrease in enthalpy. Okay, so this is, I'm glad we got to this one because recall the equation for Gibbs, change in Gibbs free energy. What is it? Delta G equals delta H minus delta S times temperature. So one way to think of the delta S times temperature, change in entropy times temperature, is think of temperature as empowering the effect of entropy. So if the entropy change is positive, it'll push the reaction forward. If the entropy change is negative, it'll push the reaction backward toward reactant side. And whichever it is, positive or negative, pushing the reaction forward or backward, respectively, the temperature is going to exacerbate that effect of entropy. It's gonna serve as like a multiplier for the effect of entropy. A higher temperature will empower entropy more to either push the reaction forward or backward. So if reaction is product favored at high temperature, that means a temperature where entropy's effect is supercharged and very empowered. So whatever entropy at a high temperature, entropy is getting its way. So that would mean that that the entropy change must be positive. Entropy must be increasing for this reaction. Reaction must be product favored if you guys should know this one. Okay, in one of your last slides, I think it talks about using burning glucose to do some biological work, and the maximum amount of work that can be done is the change in Gibbs free energy for that reaction of metabolism of glucose. But in this case, we have a reactant favored reaction, whereas doses of the product's favorite reaction. I think last semester we talked about forms of energy, and we talked about a diver climbing up to the diving board, and as he climbs up, his potential energy increases, and as he falls down, he goes faster and faster before he hits the water, and his kinetic energy increases, and then after he's in the water, his he comes to his breath, and he has no kinetic energy anymore, and he's low down again, and he doesn't have any potential energy, and we saw that his energy must have been converted to thermal energy and warmed up the pool just a little bit. So the moral of that story is that energy tends to be converted to thermal energy over time. I think we've covered enough to let you guys do this one. Remember, there's two things that drive a reaction forward: being exothermic or entropy increasing. What's going to happen when the balloon pops and carbon dioxide goes everywhere? How's the order going to change? It's going to get more, more organized or not, or more disordered. Oh, this is a good one that makes you think a little bit. Spontaneously. Let me ask you, what does that mean about delta G? Is it positive or negative? And if the solution gets colder, does that mean enthalpy is driving this dissolving process to happen spontaneously? Is it enthalpy that's doing that? Well, you guys, if you don't know these, you can find them in the slides or Google them. Okay, what do we know about a reaction if there's more moles of gas on the product side? It means that there is more disorder. Things have been broken apart. There's more little pieces that are flying around everywhere. More disorder means more entropy. So if entropy increases during this process, and we want this to be a product favorite process, we want to empower entropy to push the process toward the product side. So how do we do that? At high temperature. The change in entropy gets multiplied by the temperature. In that reaction for Gibbs-free energy change. And the last one, think about two things. Entropy increases as you go from solid to liquid to gas. And the other thing, I think that was it. And by this time, you should know whether an increase in entropy drives the reaction forward or backward. And yeah, that's about it. Good luck.